Hey, welcome to the 31st session of the Flipped Classroom for AP Calc. Today we're going to talk about Riemann sums and definite integrals. This is part 1 of section 4.4. The first thing, let's get some notation out of the way. Sigma notation is a way to express a large sum of many terms in a condensed form. Okay, here's an example. We use the Greek letter sigma to represent the summation. Here, this is called the index, and this is where the summation starts. We're starting at the first term, and we're going to the nth term. We can use, usually they use I or K or maybe J as the index number. So the summation of AK is just A to the subscript 1, the first term plus the second term, all the way to the nth term. Okay? If we used x's, another way to do this would be the summation of x sub I, and it would be x sub 1 plus x sub 2 plus x sub 3, yada, yada, yada. Here's an example. Let's say we have the summation of k equals 1 all the way to 5. Okay, k starts at 1, it tells us, and all we do is we add 1, kick it up 1, kick the counter up 1, add 2, add 3, add 4, add 5, and this comes out to be 15. A neat way to actually know what the value of this sum is without actually adding them up, if it's just the summation of x, it would be n times n plus 1 divided by 2, where n is your top order. So let's try that. N is 5. N plus 1 is 6, so 5 times 6 is 30. Divide 30 by 2, and lo and behold, you would get 15. Later on, if you take advanced calculus or some other math courses, you will learn different summation formulas. Here's another one, okay, a little more complicated. Let's say that we've got the summation from 2. Notice the index doesn't always have to start at 1 to 5 of m sub I times m sub I minus 1. Okay, so just put the initial value in, do what it says, kick it up by 1, and when you add up all these terms, you would just add these terms up, and I'm not sure what that adds up to be, but you see how it plays out. Another one, let's say we start from 3 to 7 of m squared, square 3, square 4, square 5, square 6, square 7, add them all up, and that's how you do it. Okay? The last one is 1 over m, and you can look at that and see what's done. Pretty simple. Riemann sums, what are they? A Riemann sum is an approximation of the area under a curve. Okay, and it's found by adding individual areas of rectangles stood on end under the curve. Now, you've done a little bit of this already in section 4.3, where you were estimating with finite sums, and this is an extension of what you've been doing in 4.3. The bases of the rectangles are equal to the width of some subinterval created by dividing or partitioning, there's a new word, the closed interval AB on the x-axis. These bases may be of equal length or unequal. Usually we make them equal length, but in a Riemann sum they don't have to be equal. In fact, the definition is predicated on the fact that they're not equal. The heights of the rectangles are found by taking some arbitrary value in each subinterval. We're going to call that value c, and using f of c, the function value, as the height. The graph on the next slide may make things a little clearer. Okay, so here we have a function. We have an interval a to b, and what we've divided it up into a certain number of rectangles. Notice that these subintervals are not equal. Okay? The first subinterval from x0 to x1 is a rather large rectangle. We've picked some arbitrary value. This picture calls it x1. I've added the c sub I because that's a more common notation. Okay? And that's just a value in the subinterval. And what you're going to do is the height of that rectangle at C1, which is right here, f of ci, would be the height of the rectangle, okay? So you would take that height times the width of the subinterval, and that would be the area of this rectangle. And you would do that for each and every rectangle under the curve, add them all up, and you will get an approximation of the area under the curve from A to B, okay? Questions that come to mind. Do the bases of each rectangle need to be equal? Well, we touched on this already. No, they don't, but for simplicity of calculations, they may be. Does CI need to be in the same position for each rectangle or subinterval? No, it can be anywhere in the subinterval. Okay, it's just an arbitrary point. However, many times CI is chosen as the left or right endpoint of the subinterval or even the midpoint of the subinterval. Okay. This is actually a formal definition of a Riemann sum. I think your book uses the term S of n. Okay, it's the summation, here's our index, our counter, from I1 to some term n of x, f of x sub I, that could be f of c sub I, times the width of the subinterval. So what that says is we're going to sum all these rectangles and add them up, and that is the definition of a Riemann sum. Note, a Riemann sum, right now we're really talking about positive values, but it can be negative. However, when we talk about area under the curve, that can't be negative. Okay, that's a preview of something to come. So here's some pictures of Riemann sums. We've taken a simple graph, a straight line. Okay, we're using the left-hand endpoints here as c sub I, and you can see the rectangles in the first case are, for a positively sloped line, are clearly an underestimate of the area. Okay. On the right-hand side, if it's a negatively sloped line, okay, over here on the right-hand side of the picture, we're still using left-hand endpoints, but notice it's a overestimate. So like I told you in class the other day, it isn't always going to be over if you use a left-hand endpoint, or it just depends which way your curve is sloped. Here's a right endpoints, okay? Notice on a positively sloped line, if we use the right-hand endpoints, the rectangles are too big, overestimate. If we on a negatively sloped line, the rectangles are too little, an underestimate. Okay? The norm. Other than being a character in Cheers, and you guys are too young to know that as a joke, the norm is the largest subinterval in the partition, denoted by the symbol double lines, P double lines, two double vertical lines. Okay, what does that mean? Okay, well, here's a partition of the interval, a dividing up of the interval, if you will, of A to B. Notice, this rectangle has the largest base. This would be the norm. It is the largest subinterval in the partition. That's all we're saying, and we're going to use that in a minute here for the definition of a definite integral. Okay? The definite interval is defined as the limit, counter once again, I equals 1 goes to n, of f of c sub I, those would be the heights of the rectangle, times delta xi, the base of the rectangle, okay? As, okay, and this image uses a different notation for the norm. They say maximum delta x sub I, that would be the norm, goes to 0. Okay, this is powerful. Think about this. If the largest base of a rectangle in your partition, if it goes close to 0, what does that imply about the number of rectangles that you have in your partition? Okay, this is kind of an intuitive thing. In other words, if I break something up into 3 rectangles and I keep making the largest one smaller and smaller, do I get more rectangles? Think about that. Okay, some terms that you need here to identify in the definite integral would be the upper limit of integration, that would be b, the right-hand endpoint of the interval, the lower limit of integration, a, f of x is called the integrand, dx is the variable of integration. Okay? Here's a sample problem. Let's say we've got an interval, closed interval, -1 to 3. We divide it up into n subintervals of equal length, n over 4. An easy way to get this is delta x, the width of the subintervals, equals b minus a over n. Okay, so if we take b minus a, okay, and we take this and divide it by n, that will give us the width of subintervals. And actually, I see in this should really be 4 over n. That's a typo. It should be 4 over n because we have 3 minus a minus 1 is 4, and in this case we have 4 rectangles, and so we're going to have a delta x of 1. Okay? Let's let mk represent the midpoint of the kth subinterval. Okay? So in other words, we're not using left-hand endpoints, we're not using right-hand endpoints, we're going to use midpoints. So it says to express the limit, n goes to infinity. Now notice, we're not talking about the norm going to 0. We're saying the norm going to 0 implies that the number of rectangles is infinite. Okay? So we're going to take the limit of, as n goes to infinity, of 3 midpoint value squared minus 2 times the midpoint value plus 5 times delta x, okay? And delta x here is the width of the subinterval as a definite integral. Okay, the way you would write that then is it's the definite integral from a to b, okay? So that would be from -1 to 3 of 3x squared. Okay, we're replacing the mk with x minus 2x plus 5. So we're saying that this limit, okay, of this Riemann sum here is equal to the definite integral. And so that is the formal definition of, whoops, I'm sorry, that is the formal definition of a Riemann sum. A Riemann sum, well, it's the formal definition, I'm sorry, of the definite integral. The definite integral is the limit as n goes to infinity of the Riemann sum f of c sub I times delta k. And f of c sub I would be represented by this function, and delta x would be represented by this function. Did I say delta k? I meant delta x. I'm sorry. Okay. Area under the curve. The definite integral from a to b is the area under the curve from a to b. Area under f of x, here's a equals x from a to b. Let's do an example, okay? So what I've done here is I've just drawn the function y equals x. That's this line. I've picked out an interval a, b, okay? We can think of this area under this curve as the definite integral of x from a to b, okay? And that would be equal to the area, in this case, this is a trapezoid, and if you remember, the area of a trapezoid is the area of the top base plus the area of the bottom base divided by 2 times the height. Okay, so let's look at this for a minute. The top base here, its length would clearly just be a, because we're at a, and since y equals x, the height would be a also. The bottom base, since we're at b, and since y equals x, that's our function, its length would be b. Add those together, divide by 2, take the height of the trapezoid, which would be b minus a. Okay? So in this case, we're using a geometric shape to find the area under the curve. A question for you is, what do you get if you FOIL out a plus b times b minus a? Let's do that and bring that to class, and we'll talk about that, because that's kind of a preview of something that's very important in calculus that we will talk about in another section. Just multiply a plus b times b minus a and then divide by 2. Tell me what you get. Okay? Here's some practice problems. Page 372 to 373, 1 through 22. All they are is just taking sums and putting them in integral forms and then using geometric shapes to find the area under the curve. They're pretty simple. Okay? See you later. Bye.